Hello everyone and welcome to my talk. So today I'm going to be talking about my Masters by Research project, which is titled Investigating Deccan-Induced Environmental Changes Prior to the Cretaceous Paleogene Mass Extinction. This is a project I'm doing here at the University of Edinburgh with my primary supervisor, Professor Dick Croon, and my co-supervisor, Dr. James Barnett, who is a postdoc at the University of St Andrews. So I want to take you back 66 million years ago to the end Cretaceous. And this was a really dramatic time in our planet's past. We had not one, but two catastrophic events going on in a short pace of time. So we had the collision of a 10-kilometre wide asteroid, known as the Chicxulub impact, and also the eruption of a more than 1.5 million kilometre cubed emplacement of lava, known as the Deccan Traps Large Igneous Province. So to put that into some context, the Chicxulub impact was about 66.2 quadrillion times larger than the recent meteorite that fell in Winchcombe in England. This was the size of a city. Equally as impressive, at its fullest extent, Deccan volcanism was the equivalent of 108 million times larger than that of the most recent Icelandic eruption. So we have these two catastrophic events going on at the end of the Cretaceous. So what did these do to the greater biosphere? So researchers have looked into this, and one study, for example, is the Keller and Abramovic in 2003, had observed significant changes in the size and diversity of planktic flora and minifera in some ocean drilling sites like 525A, which is in the South Atlantic. And you can clearly see here in this image a clear size change to smaller dwarfed forams, and these authors state that this was due to environmental stress that preceded the Cretaceous Paleogene mass extinction. This is further supported by more recent work by Keller and other authors in 2020, which used the reduction in global trincanids from the Els site in Tunisia, and they attribute this decrease to be due to Deccan volcanism. Despite this, however, more recent studies by Cerenza and others in 2020 compared and contrasted the varying effects on the environment that the Chicxulub impact and Deccan volcanism would have had, and these authors concluded that only the Chicxulub impact-induced winter was only able to decimate the non-avian dinosaur habitats. And you can clearly see this here, with a modest solar dimming of 10% was sufficient enough to decimate all dinosaur habitats globally. So despite these diverging interpretations of the end Cretaceous paleoenvironmental conditions by both Cerenza and Keller in 2020, it still remains widely accepted in the scientific community that the Chicxulub impact is the main driver of the Cretaceous Paleogene mass extinction and responsible for the extinction of the non-avian dinosaurs. Despite this, however, significant gaps in research concerning the preceding Deccan Trap volcanism still remain. For example, was the late Maastrichtian warming event driven by Deccan outgassing? So, a study by Barnett and others in 2017 using ODP-1262 in the South Atlantic was used to suggest a causal link between Deccan Trap volcanism and the late Maastrichtian warming event, a hypothermal event which commenced approximately 340,000 years before the Cretaceous Paleogene boundary. And these authors use several lines of evidence to make this connection between Deccan volcanism and this late Maastrichtian warming event. For example, the late Maastrichtian warming event commenced during an eccentricity minimum, a period when the Earth was far away from the Sun, so we can confidently rule out an orbitally induced cause for this hypothermal event. Equally, the authors also used the fact that we had a muted carbon-13 isotope excursion at this time, which the authors interpreted as evidence of a mantle source of CO2, suggesting, again, a link to Deccan volcanism. However, other authors have disagreed with this interpretation since, and argue that the first pulse of Deccan volcanism just didn't emit enough CO2 to drive the late Maastrichtian warming event. So what other environmental impacts has been proposed for Deccan volcanism? So significant ocean acidification has also been argued by other authors to be a consequence of Deccan volcanism. But when we look at the high-resolution records produced by Barnett in 2018, during the late Maastrichtian warming event, We only really can see identified precession amplified dissolution episodes within ODP1262, with kind of very dramatic fluctuations within the calcium carbonate content through this time. Despite this, however, a number of other sites have been used to suggest that significant ocean acidification did occur during the last few 100,000 years of the Cretaceous. So the question remains, would other acidification proxies agree with the existing iron intensity and percentage calcium carbonate data from ODP1262? And this leads me on to the aim and objectives of my research project, which is to quantify the changes in climate and carbonate chemistry that occurred during the late Maastrichtian warming event, this period here, just after the chrome 30N, chrome 29R boundary. And I have three objectives, but for the purpose of this talk, I'm going to focus on my primary objective, which is to determine if ocean acidification occurred during the late Maastrichtian warming event, and I'll be using boron calcium trace element analyses to answer this question. So let's talk a bit about the methodology. So boron calcium trace element analyses is a proxy that has been effectively used in making statements about ocean acidification in the geological past by various authors. And the proxy works a bit like this diagram here. So we could imagine a scenario in which the Deccan Traps is erupting and outgassing a large quantity of CO2. CO2 would then enter the atmosphere and be largely absorbed by the oceans. As CO2 is known as a weak acid, it will acidify the oceans, causing a drop in pH. This drop in pH will correlate also to a decrease in borate ions, and this will be recorded within the trace element ratios within the tests of calcifying organisms like this benthic foraminifera here, Natalidis trumpii, which will be the target species for my study. And we would expect that increasing CO2, decreasing pH, and a decrease in borate ions would result in a decrease in the boron to calcium ratio in benthic foraminifera. At the same time, we would expect the chemical gradient of the ocean, the lysocline, to shallow. The percentage of calcium carbonate would go down, but increase the iron intensity within the cores. So this has led me to my primary hypothesis, which is that new boron calcium trace element data will record ocean acidification during the late Maastrichtian warming event in ODP1262. So how did I come to analyse the core? What was the step-by-step process? So it started off with forearm picking of the target species Natalidis trumpii from the core material. The core material was sieved between two size fractions, 212 and 150, and then placed on microscope slides for examination. The samples were subsequently grouped into groupings of approximately 20 groups, each composed of about approximately 30 specimens of Natalidis trumpii, so we had enough calcium carbonate to then use in our analysis. Samples were then taken to the clean labs within the University of St Andrews, which they were then subsequently crushed, cleaned and dissolved to then measure the boron calcium trace element ratios. Running the boron calcium trace element ratios was performed on this triple quad ICP-MS mass spectrometer, which is used at the University of St Andrews. And the preliminary results are the ones you can see here in this graph, compared against the existing Delta 18O proxy data from Barnett et al. 2017. So a major thing to point out here is that the trends in the preliminary boron calcium data lie out with the margin of error. So we can clearly see that trends such as this gradual decrease during the onset of the event lie out with the margin of error. Also, these preliminary boron calcium data appear to agree with existing oxygen isotope data. When we expect negative excursion in oxygen 18 isotopes suggesting warming, we expect to see a decrease in the boron calcium ratio. However, we have this significant decrease of about 49.31 micromole per mole of boron calcium towards the peak of the event, suggesting potential ocean acidification caused by Deccan outgassing. However, further sampling across the peak of the event is required to support this interpretation. And what is the implications of all this? Well, the preliminary data of this research project is beginning to quantify the environmental changes that occurred during the late Maastrichtian warming event. And with this preliminary boron calcium trace element data, implying that ocean acidification may have indeed occurred during the peak of the Lake Maastrichtian warming event. So the results of this study will better help us understand the possible long-term environmental consequences of our current climate crisis if society continues to allow emissions to rise. And this is clearly shown beautifully here in this diagram by Westerhold et al. In 2020, which shows a high-resolution paleotemperature record of the last 66 million years. What we can clearly see is that under some climate scenarios, such as RCP 8.5, society has the potential to warm temperatures to reach that of the Lake Maastrichtian warming event by the year 2300. So thank you for coming along to my talk. I'm happy to take any questions as well. Thank you.